All right, welcome back, everyone. In the last video, we talked about probability and we just introduced the ideas of probability and how to calculate theoretical probability, the differences between theoretical and empirical probability. And in this section, I'm going to show you a rule about probability and how to use some of the things that you learned in the last section to answer some other questions. But I'm also going to show you something that people mistake a lot of the times. And so we're going to try to clear up a few things as we go along. First of all, in the last video, we talked about events, right? Each one of those events, like flipping a coin, rolling a die, any of those things, we would call those simple events. Okay, simple, one thing, right? Just a heads or tails, right? One coin flip. Okay. A compound event is anything that consists of two or more of those simple events. So we put two things together. So we might flip a coin and we're going to roll a die. And we want to know what's the probability that we get heads and an even number. Something like that. So that would be a compound event. When we are trying to find the probability of compound events, we have to consider a few other things. Okay? And it's you have to think about how you are counting things is really the main issue that people run into. Okay? One thing that's common for you to see here, and I know that there's some problems with these, and I want to make sure that I show these to you, are what are called contingency tables. They're sometimes called crosstabs tables or cross tables or something like that. But in this case, it's just a way to show multiple categories, counts in multiple categories of data in different groups, right? So here we could figure out the people who are likely to vote and who favor something, and those who are likely to vote and who oppose something, and those who are likely to vote and who are undecided, okay? Or, not likely to vote. And so these are all counts. If we wanted to know how many people were surveyed in this case, we'd have to add all of these up. Okay. So basically what a contingency table shows is just a breakdown of groups into different categories based on their counts. Okay. But you have to be careful with tables like these because if you're not, you can count things twice or make some other types of mistakes. So we're going to talk about those. First, let's talk about a compound event. In an aquarium, there are 10 fish. There are 10 large fish, okay, and there are 5 small fish. Half of the large fish are red. Okay, so there are 5 red large fish. Half of them. Okay, we're going to randomly select one fish. What's the probability that it's large and it's red? Okay, well, we know there are 15 fish total. 5 of them are both red and large. We figured that out from what we have here. So 5 out of 15, which is 1/3, or 33.33%. Now, this is a simple compound event, but we can talk about things that are slightly more complex. So on a certain day, a cheese packing facility packaged 500 units of mozzarella cheese. So that's our total. Okay, some of these had major flaws, some had minor flaws, and some had both. And so here are the results that we see here. Find the probability that a randomly chosen cheese package has a major flaw. Well, we know that here's our major flaws. Okay. And these are the ones with minor flaws or no minor flaws. So out of our major flaws, right? There are 24 plus 38. Okay, divided by a total of 500. 62 over 500, which is equal to 0.124 or 12.4%. And so the probability that you choose some, that one of those packages has a major flaw, right? So which is what you see here, be 12.4%. Okay, and of those major flaws, they either have a minor flaw or they don't. Okay, so let's look at the next part of this. Let's find the probability that a randomly chosen cheese package has a major flaw and a minor flaw. Well, if we want to know about both, well, that's on the table for us, right? Minor flaw, major flaw. There are 24 of those. Okay, 24 out of the total of 500. And if you divide that, you get 0.048 or 4.8%. So there's a probability of 4.8% that if we randomly chose a package, it would have both of those flaws. Okay. So let's look at the last part of this. Okay. Find the probability that a randomly chosen cheese package has a major flaw or a minor flaw or both. Okay. Well, we know that those who have a major flaw are here. And so there are 24 plus 38 of those with a major flaw. Okay. Let's write it like this. So the probability of having a major flaw, 24 plus 38, that's 62 over 500. That's what we did before. We're going to stick with fractions for just a second. We'll convert them to decimals when we're finished. Well, in fact, I even want to back up this just a little bit to you guys. Let's see, this is 24 plus 38. Okay, so that's our probability that we choose a major flaw. Let's figure out the probability that we choose a minor flaw. Okay, well, a minor flaw, that's here. And so the probability that we choose a minor flaw would be, in this case, 24 plus 51 divided by 500. Okay, and so, or both. So here's the thing. We have the probability that we could randomly choose a major flaw. We have the probability that we could randomly choose a minor flaw. Obviously, we've counted both of these here. And so both are counted in there. And this is where people will make mistakes, because this is where they will stop. But notice something really important here. We're only counting the ones that have one type of flaw, right? So either they have a major flaw, they have a minor flaw, or they have both. Which means we're only counting the ones, well, which actually means that if we do it this way, we're counting the ones who have both twice. That 24 is in there twice. Okay? And so we can't do that, right? We can't count it twice when it's only accounting for one. Okay, and in fact, you know, you could solve this a slightly different way by just adding these three groups up. Okay, but I wanted to show you something different about it. Because what happens here is we have to then subtract away the ones that have both, the probability of major and minor. right? The probability that they have both. We would want to subtract away essentially 24 over 500. That would get rid of one of these. I mean, well, my algebra's not great there. But if you write this out, and if you wrote each of these fractions out, 24, not gonna, right? One of them is going to cancel out. And you're left with only counting it once. And if we add all three of those up, you would get 113, kind of out of space over here, out of 500. And so the probability of a major or a minor, right? So it could be either one or both. The probability of that, right, is going to be 113 out of 500, which is 0.226. And again, we could just add them all up and get the groups that way. Okay. But in other situations, right, you may not have that option. Okay. And using this general addition rule that you see here, there's actually a lot of other things that you can do without having to be the contingencies tables, without having to know everything all the time. And so we're going to do some of those examples here in just a second. And so this is what you saw at the end, right? If we want to find the probability of one or the other, we add up the probabilities of them individually and subtract away the probability of them both. In math, this little upside down U here is an intersection symbol. Okay, and so this is A intersection B. What this implies is A and B, essentially. Okay, then you subtract the numbers that are in both. This is A and this is B. We just would generally use a symbol here, but that can be a little confusing here. And so the symbol for OR is the union symbol. Okay, so you'd have, but that can get a little confusing with the word OR and with this other symbol. Okay, so which one's OR and which one's AND? So we'll use OR and just stick with the intersection symbol for AND. In a recent semester at a local university, 600 students enrolled in Stats 1 and Psychology 1. Of these students, 82 got an A in Stats, 72 got an A in Psychology, and 42 got an A in both. What's the probability that a randomly chosen student got an A in Statistics or Psychology? Right? And so we can again do this in a very similar way, right? We want to find the probability of, A or B. Okay, and in this case, event A is they got an A in statistics. Event B is an A in psychology. And well, the probability of A plus the probability of B. Okay, but then we have to subtract away the probability of both. Okay, and so we want to know the probability that they got A or B. Right, well, 82 out of 600 made an A in statistics. 73 out of 600 made an A in psychology. Okay, and if we want to subtract away the probability of both, well, 42 got both. So we would subtract away 42. Okay, that will give you, if you add up all of these values, 113 over 600, or 0.188. Should be 2 eighths at the end. So 18.8% got either an A in statistics or an A in psychology. Okay, we can't just use these to calculate that probability. right? Because this probability alone would be too high. We'd be counting the people who got A's in both classes twice, like what you saw here, right? We could make a contingency table with that data, right? And it would look very similar to this. And you just have to be aware and be careful not to count the and part twice. And you want to subtract that part away. In a kitchen, we have the following drinks: 6 bottles of soda, 7 cans, 10 bottles of juice, 6 cans of juice. We're going to randomly choose one of these drinks at random. What's the probability that she chooses a bottle or that it's a juice? Okay, well, the probability, let's say that a bottle is A, right? Bottle or can is A. Okay, and trying to figure out where I could write that. Bottle or can is A, that's your choice, right? And then soda or juice is your other choice. And so A or B, those are your two events. And so the probability of A, again, I'm just going to write this formula because it helps you to remember the last part. The probability of A, the probability of choosing a bottle, there are, let's see, the total 6, 7, that's 13, 23, 29, yeah. There's a total of 29 drinks, okay. There are 16 bottles, so the probability of choosing a bottle, 16 over 29. The probability of choosing a juice, well, there's 16 juices. (16 over 29). What's the probability of choosing a bottle and a juice? Right? What's the probability of choosing both? We have to subtract that away. Right now, we've counted that twice. Okay, well, there are 10 bottles of juice. There are 10 that are both, A and B. And so we subtract 10, 29, that's 32 minus 10, 22 over 29, which is 0.759. So here's the thing to notice here. If we only use the first two, and we forget about the fact that we counted them twice, you get 32 over 29, which is greater than 1. This won't happen. That's how you know you made a mistake. It just won't happen. Okay. A retail shop accepts cash or checks. 36% carry cash, 32% carry checks, 3% carry both. What's the probability if we randomly choose someone that they're carrying checks or cash or both? Okay. So one or the other. And so if we want to find, let's see, A or B, cash or check, whether they're carrying cash or whether they're carrying checks, so the probability of A or B, again, just write in the formula because it helps to remember that part at the end. The probability of A, the probability that they carry cash is 36%, or 36 out of 100. And I guess we could write it as percentages too. Let's just do that. So 36%. Okay. The probability of B, that they carry checks, is 32%. Okay. We want to subtract away the probability of both, which in this case is 3%. Okay, where they carry both of them. Because we've counted them twice in just these first two. And so that would be 33 and 32, that's 64, 65. So there's 65% probability that you would randomly choose a customer who was carrying both. One more example here, and then we're going to get something slightly different. At a particular restaurant, 38% of customers ordered an appetizer, 31 ordered dessert. Okay, 39% of all customers order an appetizer or dessert. Right, so both, sorry, or both, one or the other. What's the probability that the customer orders both of these? Okay, so here this is slightly different now. Okay, I know I kind of speed read through the questions. Okay, but now we know the percentage that is one or the other. Now we know the probability of A or B, right, which is, in this case, 39%. Okay, but remember the probability of A or B plus the probability of B. And again, write it out because it's helpful. Now look, now we know the probability of A or B, right? It's given to us. This is 39%. The probability of A that they choose an appetizer, 38%. And the probability of B, which is choosing dessert, is 31%. And this is the probability that we're looking for. We want the probability that a customer purchases both, right? A and B. Now we can do a little algebra to get to this answer. Okay, let's just rearrange this equation a little bit. And so that we have the probability of A and B on one side. And on the other side, it will look very similar. Minus the probability of A or B. And this is just rearranging the equation. We would move this piece to, this piece to this side, this piece to the other side. Algebraically, when you switch those out, their signs flip. This one becomes positive, that one becomes negative. Okay, and so we can solve this in much the same way. The probability of A and B, 38% plus 31% minus 39%. That should give you 30% of the customers will get both. They'll get both the appetizer and the dessert. Okay, another way of showing collections of data and answers to responses in surveys is to use what's called a Venn diagram. That's what you see over here. Okay, in a Venn diagram, you have here, the circles are the particular categories. Okay, and then you can see the overlap. Okay, so this would be 76 would drink both tea and soda, right? They're in both of those groups. 97 drink just tea, 187 drink just soda. And then the 64 on the outside, those are the ones that don't drink anything. Either one. Okay. So how many students drink tea? Well, that's 97 and 76. We want to add those two together. I think I have this written down, you guys. One second while I try to turn this page. If we add up 97 and 76, there are 173 students who drink both. I'm sorry, who drink tea. How many drink neither tea nor soda? Okay, well, the ones who drink neither, those are out here. And so that's just 64. Okay, how many do not drink both? Okay, well, the ones who do not drink both, right? 187, 97, and then 64 don't drink either one. You get 348. Okay, these are the ones that drink both. And there's 424 students probably could have subtracted to get to that. But again, we can do more with probability with these as well. What's the probability of randomly choosing a student who drinks tea? Okay, well, we know there are 424 students. We know that there are 173 of them from the last example that drink tea. 173 divided by 424. 0.408 or 40.8%. What's the probability of randomly choosing a student who drinks either tea or soda? Okay. Well, if we want to look at the ones who drink either tea or soda, right, the probability of A or B is going to be equal to the probability of A plus the probability of B minus the probability of A and B. Or in this case, the probability of them drinking tea, right, is 97 plus 76, or 173 over 424. The probability of them drinking soda, 187 plus 76, 263 over 424. And then we're going to subtract away the 76 who do both. Okay, and if you do that, 173 plus 263 minus 76, 360 divided by 424, 849, so 360, 0.849 or 84.9% who drink one or the other. And now, again, you could have also just counted these three and divided by 424. That would have gotten you 360 as well. Or you could have calculated the probability that they choose neither of them and then use the complement. 1 minus 64 over 424 is also going to give you 0.849. Lots of different ways to get to the same answer. Okay? And so there's no wrong way to do it. Just know the question that you're trying to answer. Finally, this week are what are called mutually exclusive events. Okay? If two events cannot occur at the same time, then we say that these events are essentially mutually exclusive. Okay, what that just means is that there are two things where the A and B can't happen, okay, at the same time. It's going to be either A or either B. Okay, so only one of these things is going to occur. Okay, and so if we want to find that probability, we would then just add those two probabilities because there's no way to have both. Okay, so I'm trying to think of a great example in terms of the juice and soda from before. Okay, but the idea is that you just can't choose both, right? You can't be from two places. In fact, the next example is actually a really good one, right? So in the 2012 Olympic Games, we have 10,735 athletes that participated. Okay, of these, 530 were from the United States, 277 and 102 from Canada. What's the probability that if we choose one at random, they come from one of these three? Okay, well, again, there's no way this would be a mutually exclusive event. Okay, you can't be both from the United States and from Canada. You can't be from both at the same time. Okay, and so because of that, the intersection part, okay, the part of the general addition rule we talked about, that's just essentially zero. You can't be both. Right? And so it's still there in the formula, but we can kind of leave it out here, and this is why it gets people confused. Okay, because we're just trying to figure out or. If we wanted the probability that we chose someone at random that represents the United States and Canada, that would be zero, because there's none of them that would represent both. Okay? If we want the probability that it's one or the other, then we just add all of those probabilities together. So let's just say it's the probability of US or Canada or Mexico. Okay? And we would just add those probabilities together. And so that's what, 530 plus 277 plus 102. And they're all going to be over 1035 or 10,735. And you'll get 909 divided by 10,735. And in this case, 0.085 or 8.5%. So there's an 8.5% chance that if you randomly chose an athlete, it would be from one of those three countries, one or the other. Okay. And so only when you can't have both, when the events are mutually exclusive, right? So like being from two different countries, only then can you forget about the and part at the end. Otherwise, you got to be careful you don't count things twice. We'll discuss probability more next week, along with how we'll start getting into how it relates to statistics. And we're going to go back to the empirical rule and revisit with our idea of probability and start to do some really fun stuff as time goes along. So if you guys have any questions or if there's anything I can help you with, please let me know. And I will talk to all of you next week.